Now, let us study about some applications of amperes law. In our day-to-day life, we use some materials. We use some devices like the speakers, or you can say the ceiling fans. Many many equipments we will use in our daily life. That devices has some coils. They have some wounded coils that actually works on the principle of amperes law. So let's see what that is. Yes. Now there are two applications we are going to study, which is of amperes circuital law. The first one is solenoid. Second one is toroid. Okay. So these are the two kind of devices which works on the principle of amperes circuital law. Yeah. So I already told you that in our daily life we use the speakers. If you open the speaker, there is a circular ring. So the circular ring, and it is actually called as a solenoid. Or if you look at any printed circuit boards, or you can call this the PCB. If you open any device, you can see some printed board on which a large number of components are embedded. They are fixed. So there also you can see some wires. So that is actually called as a solenoid, or sometimes you can also see toroid. So both these works on using the principle of amperes. So let's study one by one. So first one is that is a solenoid. Let's see the structure of solenoid. So this contains wires. Yeah. So you can see this. This is actually called as a solenoid. So solenoid means it is a device, and main application of this device which is to produce a magnetic field. So how it looks like, how it is made up of, means it consists of long wire. It has a wire which is wounded in the form of helix. In the form of helix. So the neighboring terms of this solenoid are closely spaced, and the magnetic field due to the whole solenoid is contributed by each circular ring. Yes. Let me show one more image of this solenoid so that you can easily understand. Let me take like this. Let me draw directions of magnetic field also here so that you can easily understand. Now, so see, this is the direction of current flow. I am showing only one part, which is this part I am showing here. These are the wires. It will go like this. It will go like this. It will be there. It looks like a according helical path. Okay. So this is the direction of current all through all these wires. Now let us apply a right hand rule, that is for straight conductors. For example, with the help of the right hand rule, you can find out the direction of magnetic field. So the right hand rule says that if you hold your finger, if you hold any conductor with your right hand, then the fingers will be curled around that conductor and thumb point in one direction. Then the curled finger represents the direction of magnetic field through this conductor. It will be like this. And this thumb will give the direction of current through that conductor. If there is a conductor like this, if I am holding this conductor with my right hand, then my curled fingers represent the direction of magnetic field. Magnetic field will be like this. This thumb gives the direction of current. In the similar way, you have to apply the right hand rule to find the direction of magnetic field. See here. Imagine that this is the part of this coil which is coming out of this paper, this plane. So I am holding this wire with my right hand. My fingers are curling. So this is the direction of my magnetic field here, and this is the direction of current. So the conductor will follow this path. And if I come here, then this is my direction of current. This finger represents the direction of magnetic field. You should remember that. Here, this is the direction of magnetic field. That is the direction of magnetic field. Here, if you see, this is the direction of magnetic field. This is the direction of magnetic field. I hope you understood. So while I'm drawing this, just apply the right hand rule. Try to draw the magnetic field lines so that you can easily understand. So I am taking the direction of magnetic field for all the wires here. If you apply right hand rule for all the positions, see, this will be the directions. And it will be here at this position, it will be like this, it will be like this, and here it will be like this, it comes like this, it comes like this, comes like this. So here neighboring terms are closely spaced. So the direction of magnetic field at this point, one is around this and another one is this. What is the magnitude of current? Same through all these wires. That is, when the magnetic field produced by that wire should also be same. And the direction of magnetic field will be different due to the direction of current. Current directions are different here. That is why magnetic field, direction of magnetic field will also be different, and it will be equal in magnitude. So the magnetic field between the neighboring terms will be cancelled. There will be no magnetic field between these terms because directions are opposite. Direction of currents are opposite. So here, everywhere, the direction of magnetic field is 0. Now let us combine all magnetic field here. How can I write? I can draw a line like this. You can see, I am combining all the magnetic fields. So in effective, all directions are like this. All directions are like this. This is the direction. It will go like that. Okay. Again, and other some other distance, I can draw, I can take a loop like this. This is from, these loops are called as Abelian loops, sorry, this is a directions of magnetic field, these are field lines. See here, this is the direction of magnetic field, this is the direction of magnetic field here. Similarly, you can take here also. Here, this is the direction, see, everywhere, this is the direction. See here, in between, two magnetic field lines along the same direction. As a combination I am taking. So this is the direction. See. As you move away from this conductor, there is a large space between the lines of the magnetic field lines. If I draw one more line, it will be like this. As you move away, there will be more and more space between the magnetic field lines. That indicates us that the magnetic field is going to be zero when you move away from the surface. That means here the magnetic field will be less when compared to this. Here the magnetic field that is out here. So what you can understand is as you move away from this conductor, the magnetic field will decrease. So for some situations, what we imagine that will be equal to 0. For our calculations, for our derivations, we take that the field outside the conductor is equal to 0. And here you can see the field lines are closely spaced. They will not intersect, they will not cross one another, but they are crowded at the center. That indicates us that there is a magnetic field which is very strong. There is a more strength of magnetic field present inside this solenoid. So this is what we can understand from this diagram. Yes. Now, solenoid means, I told you that it is a device which is used to produce a magnetic field. It consists of long wire and it is wounded in the form of helix. Where neighboring turns are closely spaced and each turn is considered considered as a circular loop. This looks like a circular loop, and the total magnetic field due to the whole solenoid is a vector sum of the magnetic field that is contributed by each turn. What I told you is there are a number of turns. Let me say this is the first turn, second turn, third turn. Each turn can be considered one loop, one circular loop, and each turn will produce a magnetic field at the center or some other places. So the net magnetic field of the whole element is a vector sum of the total magnetic field which is contributed by all these terms. That is called as a solenoid. Yes. So let us derive the equation for magnetic field due to this solenoid. So now in order to derive magnetic field, this looks like one very complex. We cannot it is very difficult for us to apply the Ampere's-Capital law here to find out the magnetic field. What we have to do is, let's take a cross section of this. Imagine that there is a conductor like this. We have to take a cross section. Take a one piece from the center, take another piece. So if you separate it from the center, you will get some piece here. That will look like this. Let's imagine this is a finite. Actually, it will be like this. I am cutting this position. Dotted lines. cross the lines. This is the, I told you, this is the finite one. Length of this solenoid is a finite one, that's all. So these are the dots and crosses. Dots, this is the indication for the magnetic field. So here you can say dot indicators that the wire is coming out of this plane, and cross indicators that the wire is going into this plane. So we have got the cross section here. This is the cross section. Now, in order to find the magnetic field, we have to take some Ampere loop. Let's take one loop here, rectangular loop. Like a rectangular loop, we are considered to find the magnetic field A, B, C, D. This is the loop we have considered. I told you that when you move away from the conductor, the magnetic field is going to be zero. There is a large gap between the magnetic field lines, which indicates that the field strength is weak. And if there is a crowded magnetic field lines, if the more number of field lines are in one place, then you can say there is a magnetic field is very strong. Okay. So for some situations, we imagine that the magnetic field outside the conductor is approaches to zero. So here BC is a conductor here. So along which magnetic field is zero because it is outside this conductor. And there are two more sides of this rectangle, that is AB and CD. So let's say these are the two conductors, and here the direction of magnetic field lines will be like this. See here, this is the direction of magnetic field here, isn't it? Similarly, you have to draw. Yeah, this is the direction of magnetic field D due to this. Yes. Now, see if you look at this is the direction of magnetic field. This is the element. So the angle formed between the element and the magnetic field is 90 degrees. So from the Ampere circuital law, we know that dl cos theta. Theta means the angle between D and dl. Theta will be 90 degrees. If theta is equal to 90 degrees, then it will be cos 90 will be equal to 0. Then there is the magnetic field along the side AB is equal to 0. Similarly, the DC also will get angle of 90 degrees. That is why there is no magnetic field on the sides AB and CD if the theta is equal to 90 degrees. Or you can say the line element DL and the magnetic field are perpendicular to each other. Perpendicular means 90 degrees. That is why there is no magnetic field. Then where you can have, there is a magnetic field along AB. That is your one. So let me say length of this is h. Then the length of AB is h. Where you have to find out the magnetic field. Yeah. Now, since the side BC is outside the solenoid, BC is outside the solenoid, magnetic field approaches to 0. That is B is equal to 0, which is awesome. Magnetic field along the sides and CD is 0, because elements and magnetic field are perpendicular. That is theta equal to 90 degree. That is why B is equal to 0. Then where you can have the magnetic field? Only along AB. So let me write. Now, so to find out the magnetic field along the AD, what I am going to do is, if N is the number of turns per unit length, for a very small length, there is a N number of turns here. There are a large number of turns are there in a solenoid. Let's say that for a very small length, there is a N number of turns. Then for what will be the number of turns in a length h, that is equal to N into h. For N is the number of turns per unit length, then number of turns in h is N into h. Then h is N into h. H is N into h. Yeah. Now through all this this solenoid, there is a current I. Then what is the current enclosed by this length? By this number of turns, there is NH. I is the current going through the whole solenoid. Then what will be the current flowing through this number of turns? Then current enclosed in NH is, that is the current enclosed, I is equal to M into H into I. I is the actual current. The current through this number of turns is M into H into I. Now, then magnetic field along AD is given by closed integral of B dot dl, that is 0 to h here, which is equal to mu naught times I into 2. That is a current enclosed. Now, if you integrate this, you get B into h, which is equal to mu naught times IE. Substitute the value for IE. I is equal to M into h into. So B is equal to, that is why you get B is equal to mu naught N. So this is the equation for solenoid. So for an equation for magnetic field into solenoid, it is in the same term, that is B is equal to mu naught times N into I. So from this concept, what you can understand is there is a strong magnetic field in the center. So that is the concept of solenoid.